Now we have the argument P1, P2 up to Pn. That will get mapped to our implied scale. That is, we have P1, P2, Pn being the premises, and then we have the K being the conclusion. So it's valid if and only if the preposition P1 and P2 up to Pn also implies K. It's a tautology. So when it happens that way, then we are saying that the law is what? A valid deduction. Now, when it comes to the law of syllogism, we are doing a fundamental principle of logical reasoning says that if P implies Q and Q also implies R, then automatically P also implies R. It's valid. Like what you have here. Now we have if P, we have a Q. Now if Q, we have R. That means if P is inside Q and Q is also inside R, then automatically P is also will be inside the R. So we are saying that if P implies Q and Q also implies R, then that will imply that P will also imply R. And when it happens that way, we say it is what? Valid deduction. And that law is called the law of syllogism. So let's prove that. So let's prove the above law using truth table for the argument. So we are having P implies Q and Q implies R. All implies P implies R. So we can draw the table, the truth table, to check if it is true that if P implies Q and Q also implies R, therefore P is also implies R.
Jose,
yes,
is breaking.
A question, please. Is there a question? Or somebody call, is there a question or problem? So we are saying that if you're having P implies Q, then we have Q also implies R. Then it implies that P is also implies R. And when it happens that we are saying that it's a logic, it's valid. It's valid. So we are not going to use the truth table to prove this, if it is true. So by drawing a table, we have a table just here. So let's see the table. You have P, Q, and R. Now we need a P implies Q. We also need Q implies R. Then we need a column for P implies Q and Q implies R. Therefore, going to conclusion by your P implies R. Hence, joining all this, you have P implies Q and Q implies R implies P implies R. So we are not having that. So we are not going to see we are going to have the same thing. So now, if you are having three propositions P, Q, R, it means we are not going to get 8 main what? Rows. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now, how can I know this? Now, the number of rows that you need is determined by 2 raised to the power n, where n will be the number of statements that you have. So when you have only 2 statements like P and Q, our n now will be 2. So it will be the 2 power 2, which will be 4. That's why then we have up to 1, 2, 3, 4. Then we end at the 4th row here. But if you are having it to be 3, now you have n order will be 3, therefore your 2 raised to the power is 8. Hence you might get 8 rows here. 1, 2, 3, 4, 5, 6, 7, 8. In case you are having P, Q, R, S, which is 4, now your number of rows now will be 2 raised to the power 4. which one will go? 15. So it means we get the 15 rows down here. Are you getting me? Are you getting me?
Yes, sir.
Yeah. So now we have moved from 2 P and Q. Now we have added another proposition, which is R. So we have 3 of them. It means our N is 3 here. Therefore, we have 2 power 3 with 8. And down here, we have 8 rows here. So start from all being true. Now 2 being true and false 1. You keep on just arranging them until you come to a last end where all of them are false. Good. So when P is true here, we have P true, Q true, and we have R also true. Therefore, P implies Q is also true, Q implies R also true. Now we have P implies Q and Q implies R. Now for the and, both of them should be true before it becomes true. So we have this is true and this also true. Therefore, and is also true. That's what you can see the true here for and. Now next row we have P true, Q true, and R is false. So it means we have P implies Q, both of them are true, so they're true. Now Q implies R. Q is true, R is false. Therefore, implication should be false. When the conclusion is false, but the premise is true, then it's false. So here becomes false. Now when one of them is false, if P implies Q and Q implies one of them is false and it's false. So here also false. Then we can move on to P implies R. What is P? P is true. What is R? Now R is also false, so that will also be false. And when we come here, we have to and. So with this part is false. And the P implies R is also true. Therefore, here becomes true for this. So going through all the columns, you could see that now you are saying that if P implies Q and Q implies P, then we have P also implies R. So it means if you compare P implies R, you can see true, 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 throughout. So here becomes a tautology. Here becomes tautology. Any question, please? Any question? Now, if you go to P implies Q, we have it as the fourth column here. So you have true, true, false, false, true, 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 true. Now we have Q implies R also true, false, true, false, true, true, false, true. While when you go to P implies R, P implies R, you have also true. Yeah, you have true, false, true, false, true, 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 true. So yeah, that's also that. So that implication table. Now, since the true values of the last column are all true, the argument is tautology and it's valid. Now you are saying that if, let's say, the argument is tautology, now it means that that conclusion or that statement becomes a valid conclusion. So I think we have gotten all the last column here, all of them being true here, it's tautology. Hence, the value that P implies Q, Q implies P implies R, it's valid deduction. So whenever you are using a table or for the law of syllogism, then we use the tautology one to prove it. If it's not tautology, then it's not valid. So let's move on to another example. Now let's go to example 1. Consider the following argument. S1. If a man is a bachelor he is unhappy. S2, if a man is unhappy, he dies young. X, that's the conclusion part. Bachelors die young. Two of us. Two of us. I don't think two of us. Maybe two of us.
True. So I think it will depend on the bachelor in question here.
This is why you're talking about a man who is maybe of age, but not married.
Okay.
I
Now we
don't
could say
talk
it's
about the degree bachelor, no. So you cannot answer the question. Two of us. Oh, you can't answer it.
Yeah, it's quite a dicey one, but maybe
Now, S1 is if a man is a bachelor, he is unhappy. S2, if a man is unhappy, he dies young. Therefore, conclusion, bachelors die young. Now, the argument is valid. That is this argument valid or not? Now, let's see if we can just prove it. Now, solution. Now, you are having, let's go to statement S1. You can break it down. We are having the bachelors, and then we are also having people who are unhappy, and people who also die young. So you can say that let P be what a man is a bachelor. A man is a bachelor. Now Q, a man is not happy. A man is not happy. Then we have RB, bachelors die young. Bachelors die young. So having gotten these atomic prepositions, we can now link them to what we have here and see if you are getting the conclusion in that manner. Then you can conclude. Now we are going back. We say if a man is a bachelor, so it means if a man is bachelor, it means P implies what? Unhappy is killed. So it means P implies kill. So from the S1, we are having P implies kill. Now for the S2, what can we get there? Can somebody give me the implication there? Can somebody give me the implication for the S2?
P
Yes,
implies.
Somebody should give an implication for S2. I've given you that for S1. That's why we got two main atomic prepositions. One is a man is bachelor. Other one is a man is not happy. That's unhappy. Now when we came to S2, we are having a man is unhappy. So we have the same set as this one. So kill it. And the last one we have those who die young or bachelor die young. For the conclusion part. So as we continue the first one, S1, if a man is a bachelor and if a man is a bachelor, we are talking about P. So if P, then he is unhappy the kill. But we are having P implies kill. So I'm saying you should give me the implication for the S2. Yes, Anybody?
Q implies R.
Q implies R. Why Q implies R?
The S2 we have if we have two statements. A
And one
man
is
is unhappy. The man is unhappy is Q. And
Okay. The man is unhappy,
he
they come
dies-
out a kill. And they
Yes.
dies young.
He dies is R.
So that's good. So we have P implies Q. So we are having two what implications. So let's check if it's true. Now here we are having P implies Q. And now when we are having Q implies P. Therefore, applying the law of syllogism, it becomes what? What is the conclusion?
P implies R.
P implies R. So let's go to the conclusion part and see if it's true. If a man is a bachelor, then he dies so young. So is it true? Is it valid? Is it valid, please?
Yes, it's valid.
Yes, sir. It's valid.
It's valid. According to the law of what? Syllogism is valid. It's valid. So we have the argument now. It says the P implies Q, Q implies R, now implies P also implies R. We have the law of syllogism. Hence, the argument is what? Valid. Now, having even used this one, we can also even use the Venn diagram to also prove the same syllogism law. That makes it very easy. Now, if you're having P implies Q, it's the same as P is subset of Q. When it comes to set language. So P implies Q means P is subset of Q. And if P is subset of Q, it means all P is inside Q. Do you agree that? Do you agree? If P is subset of Q, what does it mean? It means you can find all the members of P inside the Q. Are you with me now?
Yes.
Please, are you okay?
Yes, sir. Yes.
Okay.
Yes.
Yes.
Then if you have Q also implies R. That's why it's equivalent to Q is subset of R. So to me, Q is also inside R. Now we know that for a lot of syllogism, we are saying that P implies Q and Q implies R the same as P implies Q and Q implies R in this manner. Therefore, it means we have P is subset of Q and Q is also subset of R. Therefore, which are the biggest sets? PQ, which are the biggest sets?
R.
Which one?
R.
R, good. So to me, we have P inside Q and Q is outside R. Therefore, P and Q are inside R. So when we do a Venn diagram, we are not having something like this. So we have R being the biggest set coming out. Now inside that one, we have P. Now we have what? Q. So among them, the greatest set is R and the least one is P. So P will go inside and R will come outside. As you can see. So we cannot see that P now is inside Q and Q is also inside R. Therefore, we cannot see that P is also inside R. As you cannot see. That's the meaning of P implies Q, Q implies R, hence P implies R. So now we have P implies R means P is a subset of R, which is inside the set of R, hence it is a valid deduction. So from that one, P is a subset of R is true, which means P implies R, hence P implies Q, Q implies R implies P implies R is valid. So here you can even, apart from using the law of by going through a two-stage also level, we can also go by the Venn diagram. That makes it very simple. Make it very, very simple. Now let's try the second example and that the law of syllogism. Now let's consider the following argument. S1. If you study hard, you will pass the exam. Therefore, S1. S2. If Kobe passes the exams, he will go. He will be promoted. He will be promoted. Or if you pass the exams, he will be promoted. So we're having two premises. And the conclusion S is saying that Kofi has not been promoted. Kofi has not been promoted. So what does it mean? Is it valid deduction or not? So let's
look
valid or not valid. So let's
not
break down the
valid.
first statement to two what? Atomic preposition, which should be P. Kofi studied hard. Kofi studied hard. Q, he passes the exams. R, he will be promoted. According to the first two or the premises here. Because if you study hard, you pass the exams. And if you pass the exam, you'll be promoted. So you're having a three statement there. PQR. Now, we haven't come to the conclusion part. We'll come to that one later. So let's write the implications for that. So the argument is P implies Q. Q implies R. Therefore, to me, we have P implies R. That's what according to this should have been the main what? The argument. That will make it valid. But if you come to the conclusion part, the Kofi has not been promoted. So that's why we are seeing the negation of R. So we are having it as P implies Q, Q implies R, therefore P implies not R, which is outside the law of syllogism, and for that matter, it's not valid. You agree? You agree?
Yes, sir.
Yes. We are taking to S1 and S2. That's what the conclusion of the P implies R. But when you compare the conclusion to our main conclusion here, Kofi has not been promoted means P implies not R. Therefore, it is not the law of syllogism. Hence, it is not valid. In the same manner, we can also draw the Venn diagram for them. That will make it very simple. So P implies Q is equivalent to P subset of Q. It means P is inside Q. Now Q plus R will also mean Q is also inside R. So by drawing the Venn diagram, we have this. Now it means we are now having P implies R, which is P plus R is 2. But when you go to the conclusion part, Kofi is not promoted. It means P is not subset of what? R. So we have what? Or P is subset of not R. So if P is not subset, P is subset of not R, it means not R is here, therefore to be outside the R circle. So P can be somewhere here, which will be outside the R. Hence, it is not valid. So if Kofi is not be promoted, it means Kofi is outside the R circle. Therefore, the deduction is not valid. As we're moving along, we have a question. Can I ask? Now, let me leave you to try this example. So even though I've done it for you, but you try it and let's see. Now, let's consider the following argument. S1, all logicians are clever. All logicians are clever. S2, all clever people are rich. All clever people are rich. Now, conclusion. All logicians are rich. All logicians are rich. So now let's see how we can now come out. I have even done it for you here. So we have P, we have Q, we have R. So you can now write the implication for S1 and S2, and then we conclude. So try it and let's see if you can come out with the conclusion part. If it's valid or not valid. Just 5 minutes. What did you get? Is it valid or not valid?
I think it is valid.
It's valid, eh?
So it's valid. Yes, sir.
Yes, sir, it's valid.
Okay. Why valid? Why valid?
It's valid because P can be found in R. because all logicians are clever, and um, all clever people are um, all clever people are logicians, and which they are also what rich. So it makes the statement valid.
So what law are you applying?
Um,
What law are you
I'm
applying?
using the
What?
the
Is it the law of
syllogism.
Is it the law of syllogism?
Huh?
The law of syllogism.
The law of syllogism.
Mm,
Okay,
yeah.
that's good. Yeah, so I have it even for you here. So we can apply the chain rule here. If P implies Q and Q implies R, then automatically you have P also implies R. And then that makes what? The valid deduction. So it tells us with our conclusion. So P is subset of Q, Q is subset of R, then implies P is also subset of R. So from the law of syllogism, the argument is valid. Now from the Venn diagram, we're going to have something like this. So you can see that they are all inside R. Hence, it's valid deduction. You have done well. Now let's move on to another aspect called the quantifiers. Quantifiers. And the first we're going to talk about is the universal quantifiers. Now let's consider the following proposition. I. All odd prime numbers are greater than 2. All odd prime numbers are greater than 2. I. Every natural number is positive whole number. I. All quadrilaterals are four-sided figures. Now, going through these propositions, you could see the word all. So the word all, everyone, each one, anyone are called the universal quantifiers and denoted by the symbol this, like the inverted A. That. So maybe you may be reading some books or in the programming language, you may be seeing a symbol like this. I may not know the meaning of that. You don't know the meaning. So we call it what? Universal quantifier. And it stands for all, everyone, or each one, or anyone. Now the preposition I, this I, is all prime numbers are greater than 2. So all means we are taking everything. That's what we call the universal. We haven't left anything behind. All. So you are data or you are set, you are taking all the elements, you are considering all the elements. So we call the universal quantifier. So from I, we can translate that one as for every x. For every x, if x is an odd prime, then x is greater than 2. So you can just make translation for this one. So all odd prime numbers are greater than 2 means now if a number is prime, so for every x, if x is a prime number, then x is greater than 2. You can just make it like this. But in case we let P of x, it's also called the set of x. It says that x is all prime numbers greater than 2. That means we are now representing prime number greater than 2 by Px. So if you want to use the symbol, now you can use at. Now you see the symbol for all. So we call this one all x. All x. And what is x? X is what? Odd prime number greater than 2. So for all x, x is greater than 2. For all x, x is greater than 2. With the same as for all x, P of x. For all x, P of x. So for all x means, what is x? X is what? a set of odd prime numbers which are greater than 2. So for all x, P, and P is the set of all prime numbers which is greater than 2. So therefore, we can write that for all x, P of x. Or for all x, x is greater than 2. Why x is the set of odd prime numbers. The set of odd prime numbers. So we can represent all x for all prime numbers by the symbol that, and we call this one universal quantifier. That means all x, or for every x, or each x, or any x, and so on and so forth. They all mean the same thing. So note, all quantifiers and its named, all the quantifiers and its named variables are always placed in parentheses. That's why we have put them in brackets. So for all x in a bracket, now you move on. So these symbols are very, very important because I may be reading some books and they are just plenty inside. If you are not careful, just throw the book away because we don't know the meaning of that. So very, very important. And as a language IT guys, you should know all these things because at times when you are writing a code of language, you need them. Now, similarly, let's go to II. Every natural number is a positive whole number. Every natural number is a positive whole number. So you can also translate this one as for every x, if x is a natural number, then x. So for every x, if x is a natural number, if x is a natural number, then x is a positive whole number. Then you can translate it to that. Now, if you let P of x equal the set of x is said that x is a natural number greater than 0, or x is set of a natural number, x is greater than 0, you can use the shortcut or the symbol to make it for all x, x is greater than 0, to represent all these long statements. Or because we know the P of x, the statement which is saying that x is a prime number or natural number and x greater than 0, you can also say that for all x, P of x, for all x, P of x is true. Now, all quadrilaters are four-sided figures for I. All quadrilaters are four-sided. Let's see if we can now translate this one. So we can say all quadrilaters, we can say that for every x, if x is a quadrilateral, then x is a four-sided figure. For every x, if x is a quadrilateral, then x is a four-sided figure. Now with this, we can now use the P of x, meaning x is a quadrilateral and has four sides. Or we can do the L said that x is a quadrilateral and x has four sides. Therefore, going through the symbols, we cannot say that for all x, x is four-sided figure. And what is x? X is a quadrilateral. So for every quadrilateral has a four sides, which is equivalent to for all x, P of x. For all x, P of x. So we call this symbol as what? Universal quantifiers. Therefore, all, we are taking all, we are considering all the data, the elements, the data, or the universal set. We are taking all of them. Note, the universal quantifiers are subsets. For instance, the I above, we can let A equal the set of quadrilaterals, B equal the set of four-sided figures. So therefore, we say for all quadrilaterals, all means we have A implies B. So far as you are a quadrilateral, then you are under the set of those figures with the four sides. So it becomes A implies Q. and product of B, which is the same as A is the subset of B. And hence we can just draw a Venn diagram for that one, very simple one. To make it as all quadratic have four-sided figure can be represented by A plus B is equivalent to A is subset of B. Hence, we see that A now can be found inside the set of B, as you can see here. That makes it valid. Now, definition. Universal quantifiers for all. For all. So let P be a predicate over the universe S. Let P be the predicate over the universe S. Then the preposition for all S belongs S. For all S belongs S, P of X. For all S belongs S, P of S. Means we are for all S in S. For all X in S, Q of S. It's true if for every possible S in S, P of S is true. Now, if you want to know that the universal quantifier is true, that means if you are talking about for all S, that means we have to consider every value or every element of S in the domain that big of S. So for X in S, Q of S. So it means we want to consider every element in S here. So when every element in S, when it holds, then Q of S is true. That's the meaning. Now, we shall see some of the examples for that, for you to understand it well. So let's go to another quantifier. We call it existential. Existential. Now, this, if you compare the universal quantifier to the existential one, now for universal, you are considering all the elements in the universal set to see if it holds our argument. Then you conclude either it's valid or not. But for existential, we are taking part of it. So we are the quantifiers such as at least one for some, and there exists, are called the existential quantifiers. It takes part of the domain. We take part of the domain. Now for existential quantifiers are denoted by the symbol this. So whenever you see this symbol, and maybe when you are reading the book, you see this symbol, then it means something. As you're having this for all X, or for all whatever they write, so you have for all A, something like this. We are taking with all the elements, that's it, or the domain. But this existential, we call it what? Del exists. Del exists. So we have, if you have something like that, you have the symbol here X, and it's read as del exists X. It means at most or at least one of the values of the universal set should qualify or should satisfy the argument or the proposition to make it logic or valid. But if you compare this one for all at least one, or then exist to for all S, we must take every element in the universal set must satisfy the proposition or the argument to make it valid. But this one, there exists if even one of the elements satisfied, then we make it a true or statement or become a valid conclusion. So take note of the difference between the two. So the existential quantifiers for P of X is denoted by del exist S, P of S. del exists S, then P of X. So definition. Now you have an existential quantifier that exists. Now let P be a predicate over the universe S. The preposition del exists S belongs to S, P of X. Del exists X belongs to X, then P of X. It means that del exists an S in the S, there exists an X in S such that P of X is true if for at least one possible S belongs to S, we have that P of X is true. So you see that it's different from the universal quantifier. This way, if you're able to get one of them making the statement or satisfying the statement, then it becomes valid. There exists at least one or any one. But for all S, that's why every element of the universal set must be satisfied or should satisfy the statement before we can conclude that it's valid. Now, example 1. The preposition, there is a dog without a tail. There is a dog without a tail. This can be written as, now we are there exists a dog, the dog without a tail. There exists a dog, the dog without a tail. So we are using this symbol for that. There is a dog without a tail. So we are there exists a dog. Now you have a dog without a tail. So you can translate it to that. Now, example 2, we are having there is an integer between 2 and 8 inclusive. There is an integer between 2 and 6 inclusive. This may be written as there exists an integer. The integer is between 2 and 8. There exists an integer. The integer is between 2 and 8. So please don't forget the meaning of the symbol. Now, example 3. What are the true values of the following two prepositions? What are the true values of the following two prepositions? Are they valid or invalid? I. For all n belongs to what? The set of integers. For all n belongs to z greater than or equal to 2. For all n belongs to z is greater or equal to 2. It's prime n. It's prime n. So we are the n is a prime. So we are saying that for all integers which are greater or equal to 2 are prime numbers. That's the meaning of the first statement. For all n belong to z, that is the integer, belong to z is greater or equal to 2. Now, your conclusion part is what? It's prime. It's prime n. Now, I. There exists n belongs to a set of integers greater than or equal to 2. It's a prime. There exists n belongs to the set of integers greater or equal to 2. It's a prime n. What does it mean? We are saying that here too, that there is a number or there is an integer, at least one integer, which will be greater than 2, which is a prime number. Or there is a prime number which is not an integer and greater than 2 or equal to 2. So is it valid or not valid? So let's see. Now for I. For all n belong to z greater or equal to 2, it's prime n. Now it's false. It is false. Why? Because if a number is greater than integer is greater than 2, if n is any number greater than 2 or integer greater than 2, we are having some numbers which are greater than 2, which are not prime numbers. Now, example, if you take even 4, 4 is greater than 2. So it means when n is 4, now they want to say that n is 4, and that 4 is greater than 2, which is true, and the 4 is prime number, which is false. I get my argument?
Yes, sir.
Yeah, because it's for all. It means any number greater than 2 must be what? A prime number, which is not true. So we are saying that this is a false, since not every integer greater than 2 or equal to 2 is a prime number. Example is 4. 4 is greater than 2, but it is not a prime number. Hence, it is not valid. Please, I hope you are following. Please, are you following?
Yes, sir.
Good. Now let the I. That I is true. Why true? But we are saying let exist n. That belongs to a set of integers, which is greater or equal to 2, which is a prime number. Now the two is equal to what? It's equal to 2, and that 2 is a prime number. So that makes it even what true. Since we are having even 1, making it true. Therefore, I is a true statement because the del exists. So we are not considering all the elements in the set of integers, which are greater than or equal to 2. But if we can get even just 1, it makes it what? Valid. So it is true. The position says del exists an integer n greater than or equal to 2. That is prime. This statement is true because, for example, the integer 31, which is greater than or equal to 2, is a prime number. So it is true. So you see that the two statements seem to be the same, but all the symbol that changes. We have this for all n, and we have this that exists n. That makes the difference. And that also has given us the different conclusions. Example 4. Let A be the set of 1, 2, up to 5. Determine the true values of each of the following statements. A. Del exist x belongs to A. X plus 3 equals to 10. Del exist x belongs to A. X plus 3 equals to 10. Now let's see if this one is valid or not, or true or not. Now we are having the domain here, we have A here having a set of 1 up to 5. We are talking about that as this. It means even if you're able to get 1 that will satisfy the condition here, then it's true. So we are having if x is 1, 1 is in A. So if x is 1, 1 plus 3 is 10, which is not equal to 10, so it's false. If x is 2, here we get 5, it's false. If x is 3, we get 6, it's false. If x is 4, we get 7, it's false. And if x is 5, we get even 8, which is also false. Therefore, it means it is a false statement. I hope we are getting it.
Yes, sir.
Good. Let it be. Let it be. For all x belongs to what? The set of A. X plus 3 is less than 10. For all. For all. So if x is 1, we have 4, which is less than 10, true. X is 2, 5, true. X is 3, 6 is also true. And x is 4, 7 is also true. And x is 5, 8 is also true. So these are for all of them. satisfies the condition. Therefore, it is a true statement. So it is true for every number in A satisfies x plus a less than 10. Therefore, it is true. So it is valid. I hope everybody can see it in that way. Because it's very, very simple. C. Del exist x belongs to A. X plus 3 is less than 5. Del exist x belongs to A. X plus 3 is less than 5. So let's check that if it is true. Now you have when x is 1, we get 4, which is less than 5. So since you are having 1, so since we have gotten 1 even element from A that has even satisfied, we need not to go ahead. It means it is true statement. But I can say check for all. Now 2 also make it 2 is even false, because 2 is equal to 5. Therefore, we are saying that you have 1 satisfied the statement x plus 3 is less than 5. Hence, we can say that the statement is true because the del exists. They're not for all. So B now is true for every number in A satisfy that. Or that's C. True for if x is the what? X naught is 1. Then you're having x naught plus 5 is less than 5. You have 1 plus 3 is 4, which is less than what? 5. Hence, it is true. Now the last one will be for all x belongs to the set A, x plus 3 is less than or equal to 7. Is it true of us? Oh. True of us?
False.
False. Why false? Why false?
Because when you add 5 to 3,
Good.
it's
When you
greater
add 5, you're
than
going to get 8.
7.
Yeah, yeah, that's true. But apart from the 5, all of them will satisfy the condition. Are you okay? But just because it's all for all, then all of them are satisfied before they become true. So it's false. You have done well. So try this one, let me see. Determine the true values of each of the following statements where U is the set of 1, 2, 3 in the universal set. Let me give you just 5 minutes for that. Now, what is A? True or false? True or false? A. Yes, Del exist x for all y, x squared is less than y plus 1. True or false? I should leave it for you to go and try it.
Sir,
Yes,
please, personally, because of the y, I am thrown off a little. So I don't know if you can work the A so that we see how the y and then the x
so
plays
assuming
there.
for all y. So assuming if let's say we take what del exist x. So you can tell me the x when x is 1. Are you okay? Now y can take all these values, but for all y. So what can take all these values?
Oh, okay.
Okay. So when x is 1 and y is 1, here become x squared. 1 squared now is less than 1 plus 1, which is true. Are you okay? Are you okay?
Okay, sir.
But when x is 2 and y is 1, here becomes 4, and here becomes 1 plus, which is not true. So this one is false statement. So we are taking all our x and y from the same universal set.
Oh, okay. Okay, I get this, sir.
Yeah. So we are telling you the universal set means we are x and y are from this universal set. So A is false. A is false. But when x is 2, here becomes 4. And when maybe even y is even 2, here becomes 4, which is false. Now B, you can check the same thing. B, we are having x squared plus y squared less than 12. You can check that. But when you go, you can try it at your own time. Let's move on a bit. Now let's move on to methods of proof. How to prove some proposition to see if they are valid or not. And the first method, the direct proof. The direct proof. Now for direct proof, we are not going to apply the law of syllogism. We are going to apply that law, so you know the meaning of that. So here, at this point, because it's the proof, and because it's the theory, we are going to prove, we are going to have the theory, we are going to have axioms, or we are going to have a hypothesis. So it means for this one, whatever we are saying is based upon the fact, not only on the premises. We apply the premises to know if it is valid deduction or not. That based upon the arrangement of all maybe propositions, is valid or not. Do they follow in that sequential manner or not? If so, we are there valid. If not, it's not valid. But if you come to a proof means we are not going to come out. We have the theory that we want to prove it. We have the hypothesis that we want to prove either it's true or false. So here we base on facts. Facts, the premise that we have. So for the direct proof, we start from known to unknown, or what you know about your proposition. Then you base upon the available facts, and then you come out with your conclusion. That's called a direct proof. So in this type of proof, we assume that premises P is true. Then based on the available information, the conclusion here is shown to be true by valid reference. So we assume that the premise is true. Then if it is true, then based upon your conclusion, based upon the available information you have, then you can also check if the conclusion is also true. So for direct proof, it's convenient to construct a chain of statements. It is a convenient. If you have a direct proof, then it's better to have a chain of statements. That is P, P1, P2, P3, up to what? Pn. And that one will imply the Q, the conclusion part, such as P implies P1, P1 also implies P2, P2 also implies P3, and Pn implies, what? Q. So if you want to apply the law of syllogism, then you are going to have P implies P1, P1 implies P2, P2 implies P3, P3 implies up to Pn, therefore implies Q. So we can now also say that then P is also implies Q. Because Q now becomes the conclusion part. But if it happens that way, by using our old the law of syllogism, then you can say that it is true or it is valid. Now where P is either hypothesis of the theory or axiom, and each of the implication is either an axiom or it's implied by the implication preceding it, as I have already told you. So that's when it comes to proving that one, what you know about the fact that you know where to exploit it. Example, prove the following hypothesis. If x is an even integer, then x squared is an even integer. If x is an even integer, then x squared is an even integer. So we are going by direct proof. So we can get our proposition. So let P will be what? X is an integer. P is X is an integer. Q. Now X is an even integer for this one. X is even integer. Now Q will be the conclusion part. We will also say that X squared is an even integer. So we have P implies Q. P implies Q. Now let's see if it is true or it's valid. So here we have to come out with all what you know about whether x is an even integer. So if x is an even integer, what do you know about integers? Or what do you know about even integers? So we are saying that let's come out with what you know about the even integers. And you see, if x is an integer, then we can say that we can define integers, even integers, as x equals to m, where m will be positive integer. Now let's do something with you. Now I know we have the positive integers and negative integers. Are you okay? So it's positive integer, let's have everything 0. Oh, that is not part. So let's have everything 1. So let's start from 1, 2, 3, and so on and so forth. Now you are saying that for this even integer, let's make it m. You have m equal to the set of that. So to me, m can be 1, 2, 3, 4, 5, 6, 7, going to infinity, positive infinity. When we have integer, we are saying if it is positive, then we can let it be what? X be equal to 2m. That's the definition for even integers. So let's give it true. When m is 1, we have x will be equal to 2 times 1. Because m is 1. It is raining over here. So we are not having 2. Which is even number. Now when n is 2, we can have it as 2 times 2. So we have, if m is 2, we have 2 times 2. Which will be equal to 4, which is also an even number. So when m is 3 here, and we are not going to have 2 times 2, we also 6. So it means we cannot say that we can define the even integers as 2m. 2m, where m will be any positive integer. That will give what? Even integer. So I'm saying that if x is an integer, then the definition of an even integer is given by x equals 2m for some integers of m. Some means here we are talking about the positive integers. So if so, we cannot say that we have x equals 2m. That's what we know about the even integers, 2m. Like we are saying, if x equals 2m is even, then x squared must also be even. It means I must go ahead to square my x to make it x squared. And x squared means x is 2m. So you have 2m times 2m. So I'll get my x squared equal to that. This is the x m, this is the x times m, which is the same as x squared. So I get 2m times 2m. That will give me 4m squared. Now, another notion or another definition about the even integers is also that it is always divisible by 2. So if so, let's divide our 4m squared by 2 to see if you can get a remainder or not. So therefore, let's divide x squared equal to 4m squared by 2. So we have x squared over 2 equal to now 4m squared over 2. That will give us 2m squared. There is no fraction or there is no decimal here. Hence, we can say that x squared equal to 4m squared is an even integer. Therefore, you can prove that it also implies Q, which is valid. So that if you are proving from direct method, you start from what you know, and then you conclude based upon the available information, and then you apply methods. Is that okay here? Are you okay?
Yes, sir.
Now let's do another example.
Yes.
If a and b are odd integers, then a plus b is an even integer. So prove this one from direct method. If a and b are odd integers, then a plus b is an even integer. So now we know that for even integers, we have it as 2m, x equal to 2m. That's what we know about the even integers. What about the odd integers? So odd integers too, if you name that one to be, let's say, t, now it's also given by or defined by 2m plus 1. So we know that whenever you add 1 to even number, it becomes an odd number. You know that? Whenever you add 1 to any even number, it tends to be odd number.
Yes, sir.
Can you try it? If let's say we have 8, which is even, 8 plus
Yes.
1 is 9, which is odd. If you're having 20, even 20 plus 1 is 21, which is odd. So whenever you add 1 to any even number, it becomes an odd number. So if you are saying that even number is defined by 2m, then if you want to get my odd, I'll just add 1 to it. Well, I get 2m plus 1. Where m will be any positive even number or any positive integer. So assuming if we are having this one, if m is 1, so we are having 2 times 1, which is 2 plus 1, which is 3. So here becomes 3, which is odd. If m is 2, 2 times 3 is 4, 4 plus 1 is 5. It is also odd. If m is 5, 2 plus 5 is 10 plus 1, 11, which is also odd. So you see, we can now define our odd number by 2n plus 1. Because whenever you add 1 to any even number, you get an odd number. So based on this, fact about the odd number, we can now also prove that a plus b is also even number. That when we add two odd numbers, we get even number. So we are saying that let P be A and B are odd integers. A and B are odd integers. Now, careful. A plus B is an even integer. Therefore, we want to look at P implies scale. So, after I've already explained everything to you, an odd integer is of the form x equals 2k plus 1, where k is a positive integer. Now, let A equal 2k plus 1. We are based upon this 5 and we are now proving it. So let A equal 2k plus 1. Let B also equal 2k plus 1. So if 2k plus 1, which A is odd, now B is also odd, let's add them together. And that will give us A plus B, which is 2k plus 1 plus 2k plus 1. So by opening a bracket and simplify, we are not going to get 4k plus 2. 4k plus 2. Now we can even go ahead to factor the 2 even out. When 2 comes out, we are not going to get 2 outside. Now we are having 2k plus 1. And this 2k plus 1 is the same as the odd number definition, which is 2k plus 1. Or we can also say that since if you are saying that when you add, you are going to get even number. And we know that whenever you divide even number by 2, we don't get any remainder, or it's divisible by 2. So even having gotten your A plus B, we can divide by 2. So we have A plus B over 2, which is the same as 4k plus 2 over 2. And that will give us 2k plus 1, which is odd. We don't have any remainder here. Hence, we can say that since A plus B is divisible by 2, therefore, and A and B are odd integers, then A plus B is even integer. That's P implies Q. So we're able to prove that. So for this one, we base upon the facts. We base upon the facts. And then we get prove step by step from what you know to unknown. Any question, please? Here's direct way of proving some facts. Example number 3 and the direct proof. If A is a number such that x squared minus 7x plus 12 equal to 0, then show that A equal to 3 and A equal to 4 by the direct proof. Now we all know that x squared minus a squared minus 7a plus 12 equal to 0. So if we are using the law of algebra, the rules of algebra, I want to prove that a equal to 3 and a equal to 4. So it means if you put 3 inside here to satisfy this equation, you get 0. When you put 4 here, we also get 0 here. Now when it happens that way, we can even just write this one in factor form. By sending 3 to the left side, it becomes a minus 3 equal to 0. Sending 4 to the left side becomes a minus 4 equal to 0. So when you multiply the 2, we are going to have a minus 3 times a minus 4 should be equal to 0. And that one should be equal to a squared minus 7a plus 12 plus 12. So we are saying that using the law of algebra, we have a squared minus 7a equal to 12 equal to, now I go here, we have a minus 3 times a minus 4. And all of them should give you 0. Then we're having two brackets multiply, two numbers multiply to get 0. Now, what we know about the product of numbers when the result is 0, it means that if you are multiplying A and B and the answer is 0, it means either one of them is 0, or either A is 0 or B is 0, or all of them are 0. So if A minus B, A minus A times A minus 4 equal to 0, it means either A minus A equal to 0 or A minus 4 is also equal to 0. And when A minus A equal to 0, when you solve it, you get A equal to 3. And when A minus 4 is equal to 0, you get A minus A equal to 4. Hence, A equal to 3 and A equal to 4 are the roots of A squared minus 7A plus 12. Therefore, you have what? P implies Q. This is a step-by-step of solving the problem. So that's how we can prove it. Or you can prove the statement by what? Direct method. Any question, please? Is there any question? Shall I move on? So this method is very useful in the subject of mathematics. Now you have indirect method follows from the tautology. That is, if P implies Q, then we have also not Q also implies not P. I saw this one at the previous slide. We say if P implies Q, then not P is not Q also implies not P. That's the converse way. It's also true. Good. So this statement that the implication P implies Q is equivalent to not Q implies not P, not P implies not Q. That is the inverse way. But the inverse way doesn't hold. But the converse way, which is what? Not Q implies not P holds. So we have seen this one in our area slides. So to prove P implies Q indirectly, we first prove that Q is false, and then we show that P is also true. So see this one, because it's indirect. Now we have P implies Q. We want to prove it is true. Then we are going to start with by assuming that Q is false. Then we prove that P is also false. That's indirect approach method. Now I want to prove P implies Q. So by starting, we are now proving that Q is false. Or we assume that Q is false. Then we prove it. We prove also that P is also false. But for the last one, we start with the known. What you know about the past that you want to prove. Then you base upon the premises and then you conclude. But this one, now you notice that the conclusion is false. Then you try to prove the premise also to be false. Now let's look at an example and see. For any integer n greater than 2, prove that n is a prime, implies n is odd. For any integer greater than 2, prove that n is prime, implies n is odd. So we are going to prove that if n is prime, then n is also odd for any integer greater than 2. So we can now bring the atomic proposition or statement like P is what? N is prime. When you go here, you're having n is prime. Now conclusion part is what? N is odd. So we have P is n is prime. The negation now becomes not P because N is not prime. Now conclusion, N is odd. So you have Q is what? N is odd. Therefore, if negation now becomes not Q, N is even. So we are not going to base upon N is even to see if it is false or true. So we cannot write the implication as P implies Q. That's what we want to prove. But let's start with the negation of the conclusion part, which says that now you have not N, not Q. N is what? Even. So now we're not going to get the even of N. I know when the number is even, the meaning of even numbers. So we are then, let's show that Q is false. When Q is false means odd. N is even, that's not Q. So if N is even, number greater than 2, that means we have N is equal to 2M. Now you know that when a number is even number, then it's given by defined by 2M, where M can be any positive integer. But here you say that M should be greater than 2. Therefore, here M should not be equal to 1. But when M is equal to 1, we have N be equal to N, 2. So for some integers, M should be greater than 1. So if M is greater than that, N is divisible by 2 because we are dealing with integers or even what? Integer. So therefore, your M2M must also be divisible by what? 2. And N should not be equal to 2. Therefore, N cannot be a prime that we have not Q implies not N. Let's go there again. If N is an even number greater than 2, because we are not saying not Q if N is even number. But we are saying that we are taking that not Q. So we are saying if N is an even number, that's not Q. And that even number is greater than 2. Then it means N is equal, by definition of the even numbers, we have N equal to we have N equal to M. Where M now will be any positive or integer. But because we are talking about those which are greater than 2, it means M should not be equal to 1. Because when M equal to 1, we are going to get N equal to 2, which is not part of our problem now. So we have to say M must be greater than 2. So if M is greater than 2, then we can just check it. When M is 2, here becomes 4. When M is 3, here becomes 6. When M is 4, here becomes 8. So it means that if M is 2M and M is greater than 1, all the values that we are going to get are all even numbers. And therefore, none of them is a prime number. Hence, it is false. Let's go back here. We are saying P is P, N is a prime number. So not P, M is it's not a prime number. Now Q, N is odd number, not Q, N is even number. And we are now going to prove this one. So if we prove this one, it means not this one, Q is a false. When this one becomes true, the idea is a false, and so on and so forth. So when we come here, we are having we are now letting N, we know N. So if N is an even number, then that even number is given by 2 equal to n equal to 2m, where m will be any positive integer. But you have given the condition that n should be greater than 2. Hence, m must also be greater than 1. So if the integer m is greater than 1, it means any number from 2 going. If you put down here, you are not going to get even numbers. So when m is 2, we get 4. When m is 3, we get 8. When m is 4, we get 8. When m is 5, we get 10. These are all even numbers. And when you go to not kill is also the kill is an even number. So it means when it happens in that way, it means we are able to prove that not kill implies not p. And if not kill implies not p, it means that p is also implies kill. Therefore, we are able to prove it by the contraposition. Is that okay? Time is almost up. Okay, now let's look at example 2. Now we're having proof if alpha squared is an even integer, then alpha is an even integer. If alpha squared is an even integer, then alpha is an even integer. So let's come out with our statement, P and Q. P, alpha squared is an even integer. Not P, alpha squared is odd integer. Now Q, alpha is even integer. Not Q, alpha is odd integer. So we are not going to base on odd, not Q. So not Q, so alpha is odd integer. So let's start from let alpha equal the odd integer. So if so, it means we are odd integer given by 2m plus 1. That's odd for some integers of m. So here, when m is 1, we get 3. When m is 2, we get 5. When m is 3, we get 7, and so on and so forth. So it means if you say alpha is odd, then odd alpha now becomes 2m plus 1. That's our third definition. But if m is even, now if m is odd, then s squared is also odd. Or no, alpha squared is odd. So if alpha is odd, then alpha squared is also odd. Now our alpha here is 2 plus m. Therefore, what will be alpha squared? So alpha squared means 2 plus m times 2 plus m, which is the same as 2 plus m all squared. Don't forget our alpha is 2 plus 1 for odd numbers or what odd integers. So if you square alpha, it becomes I must square here also. So I'll get alpha squared equal to 2m plus 1, which is the same as alpha. Now we square it all squared. Or you can multiply the bracket by 8, the same as 2m plus 1 squared. But when you expand the bracket here, it will give us 4m squared plus 4m plus 1. 4m squared plus 4m plus 1. Now we can just even factor the common number here for the first 2 terms. You can even break 2 out. You want to see something, you can bring the 2 out. When 2 comes out, we are now having 2 into bracket 2m squared plus 2m. So if you look at what we have here, if we let 2m squared plus 2m be equal to k. So if you let all this now equal to k here, if we are not going to get alpha squared now equal to 2k plus 1. And that 2k plus 1 is the same as 2m plus 1, which is for odd numbers. How we are getting it? So we are saying if we let n equal to 2m squared plus 2m like this, then by just substitution, you are not going to get so we are not going to get alpha squared equal to 2n plus 1, because we are letting the bracket here be equal to what? N. So we can write it as 2n plus 1. That 2n plus 1 is the definition for odd number. But don't forget, we are saying not Q is what? Alpha is odd. So to me, we are now proof that not Q is odd. Or we can also say that if you want to know that 4m squared plus 4m plus 1 is odd or even, we can divide 2 by 2. So if we divide here by 2, here it becomes 2m squared, here becomes 2m, but here becomes half. So we are now having a fraction here. Hence, 4m squared plus 4m plus 1 is not divisible by 2. Therefore, 4m squared plus 4m plus 1 is an odd number. Hence, we are able to prove that s squared, or no, alpha squared is an odd number. So therefore, we are now having not Q implies not P is true. Hence, P implies Q is also true. We will now prove that alpha squared is of the form s squared equal to 2n plus 1, which is an odd number, which means that we have not Q implies not P. And so by contraposition, we are saying that alpha is even. So we see that we have proved that Q is false, thereby using not Q. And we have proved that not Q is true, therefore K is false. And for that matter, we're able to prove that if alpha is even, then alpha squared is also even. Hence, we are done with the proof. Any question or else I'm done. The time is even up. Any question?